Just as way of introduction, if you're here for the What's New and Interesting for Physics Teachers at Pasco workshop, you're in the right place. If you didn't mean to join this one, we're still excited to have you, so please stay on board. With us today, we're going to have Dan Burns giving some high quality demonstrations in physics education today. And then you got me. I am the Texas rep for Pasco. I also cover Oklahoma, Louisiana, and Pennsylvania, but Texas is where I live and where I base my office out of, and I am always happy to talk to you. Just please get a hold of me. There's my contact info, and there's some workshop files on the top right of the screen as well. You can access those, and we'll have a link for that as well towards the end of this presentation. So if you can't get it right now, we will come back to it. Now, we're curious. We want to know a little bit more about not just who you are and where you teach, but also how would you describe your level of experience with Pasco, specifically our hands-on probeware solutions and apparatus and Capstone software. So if you would, please put in the chat box, 0 to 5, what's your familiarity with Pasco and Capstone software? 0 meaning I don't know any of this stuff and I'm hoping to learn something today. And 5 being, yep, I use Pasco all the time in my labs and I'm very familiar with Pasco probeware and technologies. So if you would please put your responses to that in chat. And I think that will maybe help Dan make a couple of last minute tweaks to what he's got planned for us, just knowing who we've got today. And I'll give a couple of minutes, or not a couple of minutes, but just a couple of seconds to take a look at that still if we got some latecomers. And then I'm going to move on. Before we get started with the actual demos, we just want you to know who we are. Pasco has been around almost 60 years. Over 6 decades ago, our founder, Paul Stockstad, won the New York State Science Fair. And his Millikan oil drop apparatus that he built was so wonderfully cool that some of the judges who were actually professors of physics and lab managers that were at this competition approached him and said, this is a really high quality device. We wouldn't mind having 1 or 2 of these in our own labs. And so Paul built them. And he liked doing this so much that he started Pasco. And we've been around for, I think it's 57 years this summer. And we are now a global science education provider for not just physics and engineering, but for K-12 level biology, chemistry, environmental science, agricultural science, you name it. We have products and solutions for all of that. And we are very happy to tell you that when you join the Pasco family, we are here to support you all over the world and including Texas. And that's, I think, the most important place. And so we offer our full support for any of our solutions that you have on your campuses. So if you ever have any questions or issues, please contact me. You'll get my contact info here in just a few minutes when we finish up here. But I'm going to go ahead and turn over this whole thing now to Dan, and I'm really excited about that. So, Dan, I will now take over the chat monitoring activities.
Okay, and keep an eye on the waiting room there too. I just let somebody else in. So
Yes, sir.
The what's new part, I am going to show you some new products and things, but I'm new at Pasco. I retired from teaching high school physics after 27 years in June of 2019. Maybe that was really good timing. And started working at Pasco afterwards, and it's been a lot of fun. Mm-hmm. And hopefully the things I've picked today you'll find interesting. There's my email address. My job description is essentially help physics teachers. And so if you're having an issue with something, a lab isn't going right, there's something you're not sure if you're using it right, something with the software, feel free to contact me. Heck, I'll even help you get some vernier stuff working if we can. Because I learn when people ask me questions, I learn, and it helps me be better at my job. And there's my phone number there. And also, if you're on Twitter, my Twitter feed, I try and keep about physics education and physics. There'll be occasionally a picture of a duck or something, but in general, try and keep it useful, and feel free to check out my feed there, and I try and keep you up to date with what I'm doing here. And let's see here. So this is our ambitious agenda. We're going to look at a couple of things with the smart cart, and that's not so new. I'll talk a little bit about it. But the smart cart motor is one of our newest accessories for the smart cart, and it just opens up a world of possibilities. I will give you a rundown of 3 different things, but there are so many that we could go on about. One of our newest things is the meter stick torque set, and it's a meter stick. And you might think, wow, there's not a lot with that. I've really been excited about working with that. I'm going to show you a couple of the many things that we've done with it that makes it real easy to do some fairly advanced explorations. And I'm working on my talk for the summer AAPT meeting, the national one, and it's going to be about is going to go on. I could talk the whole hour and a half about that. And then also we have our wireless rotary sensor with the rotational inertia accessory, which is kind of a compact rotational dynamics apparatus. And I'll show you a few things. Hopefully, if we get that far, that's my goal here. So this is sort of when I'm writing labs here at Pasco, this is sort of the model that I try and fit in. It doesn't always fit for everything. Some things are more activities, but I try and get in this sort of an analysis approach where the teacher would have students get introduced to a system and develop some questions about it, and then they fix on a question and come up with a procedure to investigate, and then they try and come up with an approach that would vary just one of the parameters. If they have more time, they go further and hold that one fixed, vary something else, and then try and construct graphs if possible to look at their relationships. And at least in high school and also in AP classes, we try and get them to linearize their data, even if it's not a linear relationship, come up with a way to change what you're graphing. And this is where the Pasco software is really strong. It makes this real easy to do. And so once they get a linear relationship, they can write the equation for that and uncover the significance of it by looking at the slope and its units, y-intercept and its units, and the value of the y-intercept. And then they get a model. And then this is a part I always found my students appreciated the most was, well, how do we know if our model's right? It sort of seems to work with the data we collected. Well, now let's predict something about this system that we changed that we didn't change in the lab, or that goes beyond the range of values that we used in the lab. And then even though I'm going to be showing you there are links to lab write-ups, really having the students present their findings to each other, I think is the best way to at least have them responsible for what they did in the lab. So the smart card is not new. It actually came out 5 years ago. That's when I actually started working for Pasco part-time. They sent me one of these, and I was playing around with it in my classroom at Los Gatos High School. And I felt like the people who saw Bruce Springsteen back in the 70s, this is the future of not rock and roll, of physics education. It had all the things that I use built in, wireless, no interface needed. And hopefully you're familiar with it, but we'll be doing some things with it today. But there's a picture showing all these devices that you have in your cabinets, maybe all integrated together in one system. And the wireless really opens some possibilities that just weren't easy to do before. So let's look at one lab that we have written up. You can do this one with motion sensors and force sensors as well. The smart cart just makes it easier. So that's what I'm going to show here. And so this is just a slide for your use later on if you want to investigate this lab. The lab write-up is here. If you click on that, it takes you to our experiment library in that particular lab, but you can search for other ones. Just search smart cart and so on. The labs themselves are going to be fairly structured, but they're in Microsoft Word. So the idea is the teacher can look at it and decide, hey, my students don't need to know these steps. They'll figure that out. And so you can edit it, you can add to it, subtract, and so on. So let's see if I can bring up our system. So hopefully you're seeing video there.
Yes, sir, we are.
Okay, so that is my track here in the cubicle. And I have what's sometimes called a modified Atwood machine set up with a string attached to the smart cart. And the string is going to there's a little delay, is going over a pulley and attached to a weight here. So it's used, the same setup can be used for a lot of different things. Oops. And what I'm going to do is just release it and record using the position sensor on the smart cart. Its position is a function of time, which also gives you the ability to calculate velocity and acceleration, and you get pretty good results with that. And then I also have the string tied to the force sensor so we can measure the force. Now I'm using Pasco Capstone software. These labs are also can be done in our Sparkvue software. Capstone has more features, but then with students, more features can mean more places they can click on the wrong thing. So some teachers like the Sparkvue, which is simpler, but pretty sure everything I'm showing here today you could do it at least in some way on Sparkvue, and I have one of the demos using Sparkvue. Sparkvue has the advantage of being able to be run on tablets and phones and devices, and it's free for those. For a license for Sparkvue on desktops and computers, you would have to pay for that after a generous 180-day free trial. Capstone only runs on desktops and laptops and also has a 180-day free trial. But if you give Scott the information he requested, what name, email, and institution, he's going to send you a single user license for Capstone.
That's
and
right.
This file that you're looking at, you can download from that Google Drive folder we shared, and we'll share it again if you didn't get it. Maybe Scott, you could copy and paste the URL for where my slides are into the chat for people too.
Yeah,
so
that's a good idea. I will do that right now.
My slides, you've got these Capstone files. So I've turned the smart cart on, and so I need to tell Capstone to find it. So there it is. So it connects with Bluetooth. And so now we're good to go. And so this would definitely help students. They would have one person running the computer and one person to run the data collection and so on. I'm doing this all on my own here. Let's see if we can give you a split view there. So I'm holding it back with a weight right now. What I'm going to do is hit record and then let it go and stop it. If I can. Did I stop it before it hit? I think I did. So let's look at our data. So normally we don't want, all that. They would start it beforehand. And I have the weight swinging a little bit there. So the force reading is a little oscillatory, but the value is going to be pretty good. what I'm going to do is I have a data run that I took a little more carefully beforehand. I'm going to display that instead. It's not really cheating. We'd get good results with the other one. That's got a little ringing in it too. So I can read the force directly that was on the cart. So if I wanted to do Newton's second law, the system is just the cart itself. It's not the cart and the accelerating mass if I use this force. And so I can get the average value of the force, 0.21. It's a little less than, notice it's less than the value before I release the cart. And so that's an interesting thing to have the students investigate as well. But then I could change the mass hanging on the string and the force would change, but the mass of the cart, which again is the only thing that would matter then, would stay the same. In this case, we are in energy and we can now graph. So notice we have a position graph and a velocity graph. One way is just to have the students read using the, using this multi-coordinate tool. They can read a position and a velocity and record those over here. So distance is how far the cart went and speed is how fast it was going. So I can just drag that back and forth and measure those values.
Dan, we had a question from chat, and I think this is a really good point to bring up. How do we, and I hate for you to have to go back and show this now, but if you could just like show the smart cart, and I mean, I've got one in my picture there, but how do we choose that cart to be able to be the one that collects the data for this certain investigation? Is there an ID number, or how does that get set up?
Up here, so that's, because I'm by myself in the cubicle, so there's nobody else around using smart carts, but in a lab, you would. And you can see right here is a code number, and that is printed on the side of the smart cart as well. And if there were more of those, well, later we'll be using them. I'll turn these other guys on.
I could show my video real quick. I've got one in my hand. Hopefully you can see it right there. And
so I just turned two more on. I'm not going to pick them.
Yeah.
But you can see they showed up here under available, but the closer they are to the computer, the higher up on the list. And so it's pretty rare to have students pick the wrong ones. I've done, back when I could actually do workshops where you'd be sitting at a table and you'd be the one finding all this out on your own with your own smart carts. It was rare in a workshop to even have a group of teachers sitting right next to another group of teachers pick the wrong device. Of course, they were also looking at the numbers, and students don't always do that.
I think it's also really interesting to note, Dan, that in Capstone software, and I believe Sparkvue does this too, you can actually see the power level of the sensor that you've connected to the software. Yep. So in this case, this is a fully charged smart card. It's ready to go.
And they last all day.
Yep.
And there's a charging garage you can get where they fit in these little slots, and the students just get trained to, when they need a smart cart, they go and get it. And then when they're done, they go put it back. And people I've talked to that have whole class sets of these, the charging is not really an issue. Well, let's take a look at other ways of showing this data. Let's see here. I want to do this here.
And while you're doing that, Dan, another question came up. Can you change the data rate of a sensor, like say the force, and keep the other sensor the same? So, just calibrating and using the settings to, I guess, sort of program your sample rate.
So the data rate is down here, and it's the default is 20 hertz, and that works for most things. I usually bump it up to 50. That's something that you're given. That's one of the advantages of downloading the lab write-up. It will have suggested data rates in there, and that's one thing I have time to play around with that as I'm writing a lab. Whereas a teacher maybe just wants to say, hey, what's going to work? And then you can start there and you might tweak it if you want. Usually when I'm using a force sensor, I increase it somewhat. The position sensor, 20 hertz, usually works pretty well. So the advantage of having this data collected, students can pick the points off and do a graph of change in kinetic energy versus position. That's what I had here, and then I changed it. Distance. And they get a slope of 0.22. And if you remember, the force on the cart was 0.21. And if they're figuring out the units of the slope, well, it's joules, Newton meters divided by meters. Oh, the slope is also in newtons. So it's got a value really close to the force. It's got the same units as the force. Maybe it is the force. And the y-intercept is incredibly low in this data. And so they figured out that the change in kinetic energy is equal to the force times the distance. And so that's work kinetic energy. That would be sort of structuring it some, but you can also just have them, once they've collected the data, just start looking at different relationships. What does it look like? This is, that's the run. Let's go back to run one. So that's velocity versus position. That's kind of interesting. It's not linear. What might make it linear? So if I just click on the axes, there's a feature called Quick Calc, which we just added something similar to Sparkvue as well. And I can see what happens if I square the velocity. Oh, I got a straight line. And the slope is 1.73. And depending on the lab you're doing, they would figure out why that's significant. I think I have it over here. So this is the same graph I just did, but I added a note to it. And so if you're having them do kinematics, the slope should be 2 times the acceleration, which they could measure. Or in this lab, the slope would be 2 times the force over the mass from the change in kinetic equals force times distance graph. And in fact, they can also, if I go to the calculator here, you can see I made 2 change in kinetic energy graphs or data tables. And the second one, I'm just using the actual velocity data. So I don't have to read any points and make any data tables. I can just graph that instead. And so I called that delta K2. And I get the same relationship that I got back here. Without having to create that data table. So I have the same slope as 0.22. This one comes out to 0.219. So it's almost too easy. So some teachers wouldn't even want their students doing that depending on how far in the year it is. But the advantage of this is now they could change the mass of the cart, see if it still works, change the weight that's on the string, see if it still works, and so on. So the idea is give them data, and then they're spending more time trying to figure it out than collect it. So again, that's the basic structure of the lab, which again, you can download there. And just, that's what we were just looking at, but the print is bigger. So if you're trying to read that graph I had, this is a little easier to read. And then you can see the calculation that we entered into Capstone, and Sparkvue also has those calculations. So they can graph kinetic energy, impulse, and so on. And that's what the next one is a impulse change in momentum. And let's go back to the camera here. There we go. So I'm going to take the weight off the smart cart. And you can see I had a hook on it. It also comes with a magnetic bumper that screws right into there. But what I'm going to use, it is an extra thing, but they're not expensive, is a spring bumper. And that just goes right in there. And so now what I can do is just give the cart a shove, and it'll collide with the end stop, and we can measure the force and position, velocity, acceleration. So let's open up that Capstone file. Now it's going to ask me if I want to save anything. I don't. So when you download this file, just have that one data, not the second data collection that didn't work too well, because I'm doing this all by myself. So these are all the files that I put up on that Google Drive that link goes to. And here we have impulse delta V. And so as far as these, setting up the files and so on, what I tend to do earlier in the year is they'll open it up and they'll have a graph there or a data table ready to go. And then as the year goes on, I have them do some of it and then more of it. And by the end of the year, I'll just say, hey, you're going to be graphing force versus time today, set it up. And they will know how to do it. Or at least one person in the group will know how to do it. I got to turn that off because here we go. So I go to hardware setup. Now, because I closed one file and opened another, it stayed connected to the smart cart. Sometimes that causes problems. So normally I quit Capstone and then open it again because I'm using different sensors. But if you're using the same sensor, it's actually a good feature. Also notice the other things here. There's the acceleration sensor and the gyro. Well, I turn those off if I'm not using them, then I can make the data rate even higher. So if you are, let's say you were doing an experiment and you wanted a 200 hertz data rate, that usually is not a problem, but sometimes depending on the hardware you're using, it might have trouble. And so if you turn off the other sensors and only the ones that you have on, it can make that possible. So I do have the smart cart force sensor collecting at 200 hertz. I think this one, oops, this one I could do a little easier. Let's get them both here on the screen. So I'm going to hit record and then just give it a shove. Well, that was a pretty wimpy one, but oh well. Let's make that bigger again. And you can see as it was going in, it was slowing down a little. That's because I biased the track for the previous experiments so that the net force on the cart was pretty close to zero. I tilted it down toward the other end of the track slightly. So when you gave it a shove, it went a constant speed. And now I'm pushing it the other way. But it doesn't really affect this experiment. So you can hear it's going toward the wall, it's slowing down. Here it's staying the same speed. That was by intention. I might change that for this experiment, but you don't really need to. And so I can move the data around just by clicking and dragging. And then I can expand the scale so we can take a look at it and just look at that beautiful impulse curve there.
Dan, we have a question that came up. Is there a time delay when collecting data between multiple sensors, or do they collect simultaneously?
Well, I think we're seeing that here right now. Let's turn on the multi-coordinate tool. And the force sensor just starts to move there. And you can see the velocity just started to go down there. There's a difference in data rate between the two. And then here I have maximum force when the velocity is 0. That seems to make sense. Is it slightly off? Again, I think that's more data rate. And then here it picks up back to its speed once it goes off. So it should be synced up pretty well. And what the students would do here, notice I have the data table here, is they need to get the change in velocity and the impulse. Those columns wouldn't be filled in for them. And so the area under the curve, it says is negative 0.47 Newton seconds. Well, let's say you didn't want them dealing with negatives. You could go in here, quick calc, and change it. And so now it's positive. I think the lab, I forget what I had them do for the lab, whether they did that or not. But it's not really a problem. The impulse and the change in velocity are both negative here. So I need to get the area under that curve, but if you look, I did something wrong. Well, I didn't really do it wrong. I did this earlier. I didn't zero the force sensor right before my trial. So the force sensors are somewhat sensitive to temperature and turning on. And so a good idea is to zero it before you start collecting data. But my data was pretty close to zero here, but I'm a little off. But if I'm getting the area under all this, then that's a problem. So how do I select just the part I want the area? There's a little highlight tool here. And I can drag that around, and then it makes it real obvious that I have selected just the part I'm interested in. And so now the area is negative 0.24. Notice how different that is. If I want the change in velocity, different ways of doing it. You can just read it off the graph. But if we turn on a multi-coordinate tool, I can put it here. That's the velocity before it hit. And then I can put another one down here, or there's a delta tool. So if I click on that, and Sparkvue has this feature too, I can put it here, and it tells me the change in velocity is negative 9.43. So I fill in that data table. They would go a lot faster for them. I hit record again. I give it another shove, but maybe a little harder this time. And then I go through the same process and get 5 or 6 points where the change in velocity is significantly different. Then they can graph that, the impulse versus the change in velocity and the slope. Oh, I forgot to do this. I had an extra mass in the cart when I collected this data. And so the mass of the cart was 0.5 kilograms. The smart carts are all about 0.25 kilograms. And the standard masses that fit in them are 0.25. So it's real easy to give them collision experiments and other things where they're doubling the mass of the cart and tripling it and so on. But in this one, I did have an extra mass in it. So they have figured out that the impulse is equal to the slope times the change in velocity. And the units of the slope are kilograms. And its value is very close to the mass of the cart. So they can figure out that relationship that the impulse equals the change in momentum there. And then they could take that and put an unknown mass object in the cart and use that relationship to figure it out, or there's plenty of other things you could have them do. Well, that is, I think we just saw that. So that's old stuff, the smart cart. The smart cart motor, we attach to the end of the smart cart. And it's one of the many accessories that work with it. There's a cable that plugs it right into the smart cart. And so when you connect the smart cart to Capstone or Sparkvue, the motor is also connected as well. And if you give it a certain power level, anywhere from negative 100 to 100, it will go at a constant speed. Negative 100, it goes in the reverse, or the negative power level goes in the opposite direction. And it gets to that speed pretty quickly. So if you say start at 100, it ramps up there pretty quickly. But what's really cool about it is this power level can be set manually, but also automatically or dynamically. In other words, responding to what time it is. So you can have it ramp up or down, or you can have it respond to sensor readings. And there's all kinds of, and it works with any Pasco sensor then. And it has a rechargeable battery, and it does work off track. And so I was doing some things that people do sometimes with the constant velocity buggies with this on the carpeting in my cubicle, and it worked just fine. And it has, you can add extra masses, and there's string ties to it. So let's look at a couple of applications of it. I think I have 3 here. And one is having students discover the relationship between components and magnitude of a vector, in this case, velocity. So let's go to the video here. So I have the smart cart with motor, and then I've attached this is called a smart cart rod stand, and I've attached a wireless motion sensor to the smart cart. And what I'm going to do is put it in the corner and then have it come out toward us. And I got to turn things on here. So I turned them on earlier to show you how they show up in Capstone. Well, since I wasn't using them, they turned off automatically. So I pointed the motion sensor, the camera, at the wall. And so it's going to measure the speed of the cart relative to the wall. And if you look at this coordinate system, if we set this up here, so it's going away, in this case, it's moving in, it's measuring its velocity only along the x-axis, the wireless motion sensor. And the smart cart measures the velocity along the track, the magnitude. And then you could point the smart cart, the motion sensor at the x-axis, and as it goes away, you're going to measure the velocity along the y-axis. So let's open up that file. Let's do a quick demo. Save. So this is velocity components. And go to hardware. And so now I don't want this red smart cart. And so I can exit out. And I intentionally picked blue so I could remember which one to pick. And so it's blue, and then it does say 938-132. If I went and looked, there's a tag on it that says that. And then there's only one motion sensor, so I know it's that one. But again, it is tagged. And what I've done, so now there's a extra little control panel here, and this again also happens in Sparkvue, that controls the smart motor. So I have it so its power is 70, and I set it so it's going to stop after it goes 0.4 meters. So you can have a measurement-based stop condition or time-based. And I can also do that for the start condition. And if I hit record, so it just went a little bit. That way it doesn't run into the end or go off or anything like that. And so you can measure the angle and then look for the relationship between the magnitude of the velocity and this component. You could also use these two to figure out what the angle is. The way the lab proceeds is they measure the angle, write down the magnitude of the speed, and then in this case, what did I say? This was the X velocity, yeah. And then they would turn the smart cart, turn the wireless motion sensor to the other wall. So the magnitude here, you can pick the statistics menu here and get the mean. And so the magnitude of the smart cart's velocity was 0.375. And then down here, whoops, turn it back on. Go. And it's 0.26. And so I didn't measure that angle, but the lab goes through it and they figure out the sine and cosine relationships using that data. Now, when I was doing this, you know, I'm here at Pasco, I've got more motion sensors. And so I wondered, gee, could I put two on and measure both concurrently? So here's a video doing that. In this case, I have it going toward the corner. I figured out going away worked better, but it still works. And so I'm getting both X and Y components simultaneous there. And you might be thinking, gee, I wonder if I could do 3. I haven't tried that yet, but if you were to put a roof over the top, you can't really get it to point at the floor. Then you could also have a third dimension on an angled track or something. Haven't tried that yet. If you try it, let me know how it worked for you. Let's see here. There we go. And then another one is a standard sort of, you know, train A and train B sort of problem. We have 2 smart carts and they are going in opposite directions toward each other. Where are they going to meet? They're going in the same direction, but the one behind is going faster. Where are they going to meet? And so first the students characterize what the power setting is in meters per second. It's about power setting of 100 is about 0.5 meters per second. But if they've been using them all day, they might slow down a little bit. I usually found using that setting work for most things, but in this, they want to be pretty precise. They want to predict exactly where they're going to meet. And so what does that look like? So I put a piece of masking tape where I predicted they would meet. And it's usually within a centimeter if you put in the accurate velocities. And so let's try that out live here. And so this one I have them on the same track.
Dan, let me ask, didn't we do a Pasco live episode about this a couple of weeks ago?
We did.
Okay, I don't want to make sure I just shared the right link in the chat box. This is a longer version of it, but it's really cool. But rather you watch Dan do it right now than watch the YouTube video.
Yeah, it won't be as professionally narrated as that episode with JP there.
Right, but in case anyone wants to go back and look at it later.
So I want to open up the Capstone file. That one we're using a longer track, so that was kind of fun. To make sure I connect to the, so notice it's asking me it says, hey, a wireless motion sensor isn't part of this experiment. Do you want to connect it? I'm going to say no, because we're done with that. We're on to a new thing. And so if I quit Capstone and then open up this file, that wouldn't happen. And so I have the red one now that I want to connect. Okay, back to the slide. So yesterday or day before yesterday, I just set this up. And so I have the red cart is going to start moving at time 0 at 0.17 meters per second. The blue cart's going to start moving at time 0 at 0.11 meters per second. And they're about 0.7 meters apart. Double check that. Here we go. Got it going in the right direction. Yep. And so you can write the equation of motion for each object. Now there are easy ways of doing this too with, well, this isn't too tough. You can use the relative velocity to figure out at what time they're going to meet and where they're going to meet. But I like doing it this way because once you introduce acceleration, then this method works a lot better. So those are our equations. We put in what we know for each one. And the question is, at what time will those two positions be the same? And if we solve for it, we get 2.5 seconds. And then you just put that time back in the original equation. And here's where telling students, hey, you don't have to wonder if you're right or not. You'll get the same answer for both if you did it right. So we're predicting they're going to meet at after 2.5 seconds of motion at 0.42 meters. So let's see if we can get both things up here. On Capstone. There he is. And so what I've done, a couple of things, is I'm going to graph where the red cart is, just using the Pasco, the smart cart data. But if we go look at the calculator window, it's a little small there. What I did is I set up a coordinate system for the blue cart that's the same as the red cart. So I'm taking its position and subtracting that from 0.7. So they're both on the same coordinate system rather than their own internal one. And then for the smart cart motor, I have them waiting a couple of seconds before they go. That way, when you first hit record, it's possible that one cart would start before the other. But if you have them wait a little bit of time, then they start pretty much the same time, as we'll see. And I also put in a stop condition so that when the force sensor exceeds a threshold, it will stop them. So when they collide, they're going to hopefully automatically turn off. You know, it's the fancy little extra thing. So let's see if it works. Predicting 0.42. So 2 seconds of delay. Bam. So, oh, it didn't stop. Not sure what happened there, but pretty easy to hit stop. And so let's read that coordinate. Oh, we can make this bigger now. And so they met at 0.44 meters. I got to meet at 0.43 the other day. And so usually it's within a centimeter. I might have started the red one. Let's do it one more time. I might not have pushed the red one all the way back. So I'm just going to 2 seconds. And so it's still about oh, 0.4397. That's better. No, 0.44. It's off by a couple of centimeters, but still pretty good. Now, this is not a tough problem. They get tougher when you have acceleration, and you can program them to have a constant acceleration. And it's not a very tough code. So built into Capstone is a visual programming tool called Blockly. And so in it, I've put this little piece of code that will change the power setting depending on the time. And so I have a conversion. Well, I can make that bigger, I think. Whoops. Well, let's just go look at the code. Let's do that instead. So I'll open up Capstone. And it's going to have all kinds of things about sensors that aren't part of this. There we go. Now just the motion sensor. Which one does it want? So notice this part here, code. So if I open that up, there's that same code, but maybe a little bigger. I can enlarge it somewhat. And so the conversion factor lets me enter things in meters per second. So I'm going to have the cart start off with an initial speed of 0.4 meters per second. I'm going to give it a negative acceleration of 0.1 meters per second squared. And then I'm going to have it go for a certain amount of time. And it's a blue cart. It tells me that. And so I'm telling the blue cart that its power setting is V0 plus A0T times this conversion factor of 200, because 100 equals a half meter per second. And then I update what T is and just keep looping as it goes. So what does that look like? The blue card there. And let me take the motion sensor off. Leave the rest of that up there. That all comes off, but we'll just leave it up there for now. Okay, here we go. Record. Oh, the video isn't keeping up with the... I have it recorded. I couldn't, at least on my screen, I couldn't see the video. But let's just do it again. I'll just show you the graph. Oh. It was stuck on the pulley. So we get a nice parabola. There's a little discontinuity maybe here at the top. And then a pretty straight line with a little wiggle here when it turns around, but pretty good. The slope of the velocity, this is a velocity graph. The printing is very small here. The slope of the velocity graph is 0.11, and we put in an acceleration of negative 0.1, and it's negative 0.11. And then what about this parabola here? Well, I can do a curve fit for it as well. And the term in front of time squared should be half the acceleration, and it's 0.0575. And so it matches pretty well with what we were trying to do. Here is what it looked like with both things showing. Not sure why the video wasn't able to keep up there. And so they can put in whatever they want here. Now, of course, they're going to run into constraints. The cart can't go faster than a 0.5 meter per second, and it's on a limited length track. But that in itself kind of brings up some kind of neat things. You could have them come up with what's the fastest I can get it to travel the whole length of the track and come back to a certain point, and a lot of other things. So when I was playing around with it, not playing around, when I was working with this, I used to teach AP Physics Mechanics C, where we also go beyond constant acceleration. And so we looked at problems where there was a changing acceleration, and that can be a tough thing to do in the lab, especially if you want a constant rate of change, which would be constant jerk, right? And it turns out the code is very similar for making constant jerk, and it works pretty well. So let's take a look at that. See if the video will work better this time. So there's our graph. And the code. See if I'm also using the blue card here. So, well, let's shrink that down. Yeah, I'm using the blue. So the code's similar. So I have an initial velocity, initial acceleration, and an initial jerk. And I'm setting the others to 0, just keep it simple. But I'm setting the jerk to 0.06. And you can see I'm still just writing out that equation, which is this equation here, telling it, or this one here, I'm telling it what its velocity is based on having that setting for jerk. So let's see if we can get the video to show as we go here. Oh, it's stuck on the pulley again. Normally I'd have an end stop there, but we had the pulley for the earlier experiment. So let's try again. Yeah, the video is still too much for it. What is, do I put my hand in front of it? That's weird.
All right, Dan, I need to give us a 30-minute warning here.
Okay.
30 minutes.
We're doing good. So the data, I have a linear fit to the acceleration time graph. And yeah, it's not exactly straight. There's a little jiggle in there, but it says it's the slope is 0.059. And we set the jerk to be 0.06. And then the quadratic, this A term in front of the T squared is should be half the jerk. And then here we can fit a cubic. And the D term should be 1/6 the jerk. And it comes out to 0.0099. So 0.01 is what we wanted. Here's some slides. You can actually see that. It's really the same thing we just did. And I can show the video here. A little jerky there. Well, that's, I guess we asked for it. So if you're looking to do some interesting things with non-constant acceleration, I don't really know of anything else that would allow you to do this. So I was excited about the jerk. Let's look at something that's very new, the meter stick torque set. And it comes with a pivot, which has a pulley that can fit to it. and then a meter stick clamp that can also fit to this axle. And there's another axle on the other side, so you can have the pulley and that. And then there are 3 mass hangers that also clamp to the meter stick. So you can set up beam arrangements. Here we have a force sensor on this one, so I can measure the tension maybe after students predicted what the tension is. And it's got a lot of nice design features in it. The bearing on the pivot is really low friction for doing some cool physical pendulum experiments and things. The mass hangers have a degree scale. It's kind of a crude one, but it works for a lot of things. There's a bubble level on the meter stick clamp. And then what's really neat is the aluminum meter stick. It's even hollow. There you can find neodymium magnets that fit in there, and you can do Lenz's law experiments with it. That isn't what we're doing today. But I wrote 6 labs for this, and you can find them all by picking the searching meter stick torque set in the Pasco experiment library. And I picked a couple here. The first one, I'm using the meter stick and the clamp and the pivot to make a physical pendulum. And we're gonna measure the period, in this case for small amplitude. And then we're gonna move the meter stick clamp so that it's at not the very end, but at 5 centimeters and 10 centimeters, 15, and so on, and investigate the effect of that on the period and on the rotational inertia. And with this lab, if you look at this particular lab write-up, the students end up creating the parallel axis theorem with the data. And if you want to take it further, they now have data for period versus how far from the center of the meter stick the axis of rotation is. And so they can use calculus to solve for the location that's a minimum period, or they can use their data. So let's look at the data. There's a lot here, and let me go through it. So we'll do this as a demo in a little bit. This is just me letting the meter stick run, collecting its period over time. And so the students see, wow, period is not independent of amplitude. But down here at the end, the amplitude is small, it stays pretty constant. So they get an idea if they're moving beyond that, where it might have a significant difference. I forget what the max amplitude here was, but we'll do that in a little bit. I can even make that higher. And so this is the data they collected with the meter stick clamp all the way on the end of the meter stick. It's 0.5 meter away from the center, and they collect the period and solve for I, and then they put it to 0.45 away and solve for I, and then graph I versus that distance. And they get a parabola. And then if they graph I versus x squared, they get a straight line now. And the straight line has a y-intercept equal to the rotational inertia of the meter stick about its center. And the slope is the mass of the meter stick. So they find out the rotational of the meter stick, once I move that pivot away from the end, is the rotational inertia about the center plus this mx squared term, which is the parallel axis theorem. Then they also have the period x data that they can graph, and they see there's a minimum somewhere around 0.3 meters. And if they know calculus, they can take the derivative of the period equation and find the x position where it's minimum, and it agrees with the data. So that's a more advanced topic, and not for college, I guess. Smart students will realize that they really only need to take the derivative of what's inside the square root sign. It's a lot easier, but you got to know that. And I guess if they know that, they could have done it the hard way as well. So let's take a look at, I'm going to quit Capstone here just so we don't have all that smart cart stuff. And start it up again. So this is physical pendulum.
Dan, while we're waiting for that to come up, we got a question about the fragility of these aluminum meter sticks. What is the thickness as well, if you know that, of the meter stick's interior?
Well, you know, here at Pasco, my manager has been walking around the office with one, JP. And if you're not working
For
man,
motivation, yeah.
you know, he's not hitting us. He's hitting our table to wake us up, and those meter sticks are not dented or bent or anything. Now I have, let's see, let's go to the camera. I'm going to try something different here. Okay, it looks like the camera cut out. Oh, that wasn't good. Hang on a second.
All right.
I tried to reboot the camera.
Okay.
I don't think that's the one we want.
I think you're back up now.
Okay. So, but it's just a small view, right?
Yeah, it's instead of we're seeing you, now we're seeing the camera set up.
I'll try getting a bigger view here in a second.
Okay.
But here we have two of them set up. Let me try and get a bigger view. There we go.
There we go.
And it's live now. So something just glitched with it. That's the weird thing about doing these online workshops. I'm sure it's the same for online instruction. I never went into my classroom and worried about all of a sudden I wouldn't be able to talk, and then I wouldn't know I wasn't talking. But with Zoom, you do that all the time. Well, at least I do with the mute. And same with viewing. I always knew what the students could look at and see, but boy, with online stuff, you never know. So this is the aluminum meter stick. Whoop. See, I did that on purpose to show you how tough they are.
Yeah, we see that now.
So they just banged into that track, and it's unscathed. No, you would not want to do that typically. But what I want to do is release it from horizontal, which is a little up there, and then measure the period as it goes. And so I have a smart gate down here. It's just any photo gate works for this. The smart gate is two photo gates kind of crammed together. So you can use both beams to measure the speed of things. I'm just using this with the single period timing. So as it swings through the bottom, it'll start a timer. And then when it comes back, it doesn't stop the timer, but it registers that knowing, oh, the next time it goes through is 1 period. Then it'll measure the period. It just keeps doing that over and over. I also have up here a wireless rotary sensor. Well, for this lab, we wouldn't use that, or you wouldn't have to. You would use the pivot that comes with the meter stick torque set. But with the rotary motion sensor on there, I can also measure the angular speed of the meter stick, its angular position, and that's for the next lab. That's why I have that up, but normally you use this. So let's try here. So I need to connect to the smart gate. And let's see if we can do real time here. Now I want to make sure it's not in there when I hit record. Whoops. Oh, so this attaches in here.
And Dan, while you're doing that, a question came up. Is the pivot set included with the rotary encoder, or is it a separate purchase?
It is separate. So the meter stick torque set comes with the pivot, the meter stick clamp, and the mass hangers.
Mm-hmm.
So I've got it horizontal now. So we should be seeing, there we go. A little off the scale. I click that button for auto scale. And so with a normal pendulum, that'd be kind of hard to do, to have it go for so long, to see the period change. The period as a function of amplitude is a pretty advanced topic. What I'm doing is working on a simulation that will mimic this motion and compare it to measurements made with the rotary sensor. That's going to be my talk for the summer AAPT meeting. And so I will post, if you don't go to that, I will post that on my Twitter feed, and it'll end up on the Pasco YouTube channel at some point. That is a work in progress, so I wasn't ready to quite share all that. So we've kind of settled down to fairly small amplitude. It's kind of fun to let it go, but we have a limited time here, so we'll go ahead and stop that.
Yeah, 15-minute warning, Dan. Okay. 15 minutes.
We are doing just fine. So again, that's the Physical Pendulum Lab. And so back, just, I think I had a picture here of the, there. So all the things that come in the meter stick torque set are shown here, here, and here. And then they're all together here except for those masses in the rod. The rotary sensor is a great addition to this, or this would be a good addition to your rotary sensor if you have one, whether it's the old style or the wireless. So the Falling Beam Lab, let's turn this up a little bit. What we do is use the rotary sensor now, which I already have attached, and the students predict the angular velocity of the meter stick when it's horizontal after being released from the vertical. Now you can obviously change that. You can have them release it from the horizontal and have it measure it when it falls to the vertical. I was thinking what might be easier if they're doing it on a lab table, and if you didn't want the meter stick swinging all over the place. So I'd put a box or something here so that shows the meter stick after it's fallen. And also, if you restrict it to that particular case, you get kind of a neat linear relationship between the angular speed squared and sine theta. I'll demo. Well, let's go ahead and demo it here. So this is falling. Oh, this is the one I did in Sparklab. Just to show you Sparklab, or not Sparkvue, that Sparkvue can do all this stuff too. So we have a graph of angle versus time and angular velocity versus time. And I need to connect to the smart gate. Well, no, not the smart gate, the rotary motion sensor. You could use the smart gate too, but we're not in this case. So I practiced this before. Let's see if I can do it. So wherever I hit record, the sensor is going to zero itself. So that'll be zero angle. And you could do that in a different way, but that's the most convenient way. So normally you'd have a student working the mouse and then somebody over here doing it, but I'm going to use the bubble level to hold this thing horizontal and then click record. Try again. Okay. Now I lift it up to vertical. I guess it's sort of off the screen, but you'll see it when it comes back down, and release it. And that's just fun in itself. We don't need all that. And so one prediction you might do is how fast is it going when it's horizontal? So the angle is back to 0. And so the closest I can get is 0.006 because of the data rate, but that's essentially 0. And so it's saying the angular speed at that point is 5.65. And I'm remembering if you predict it, it's 5.8. So pretty close. And so here I have the initial angle. This is releasing it from 90 degrees or 1.57 radians. And this particular trial, instead of 5.65, I measured 5.44. Then I released it from different angles above the horizontal and measured these horizontal speeds. And if I graph the angular speed when it's horizontal versus the initial angle, I get a curve. And this is a pretty advanced linearization. You have to modify both axes. So horizontal speed squared versus the sine of the angle gives me a straight line, and the slope should be 3g. And so I get 28.7, which is pretty darn close to 3g. So again, that's the one of 6 labs for this set. When there'll be another one that comes out of the paper I'm doing for AAPT. And there's the data we just saw. And at the very end, again, this is a more advanced lab. I do this with my AP Physics Mechanics C students, or definitely a college engineering physics would probably do something like this. And at the very end, they're asked to, instead of predicting what's going to happen when it's horizontal, start it out at 1 radian and predict its speed when it's at 0.6 radians, or it's rotated through 0.6. And so this is just the math that's in the teacher version. And I predicted it'd be 2.85. And then when I did it with the apparatus, I got 2.83. And something I found when I was teaching was doing something like this and then seeing it actually agrees with what things do in nature is just powerful. It's students get blown away by that. And so we're talking about this rotary sensor. And that's gotten a lot of attention in high school lately when AP Physics 1 started, because AP Physics 1 and 2 replaced AP Physics B, and AP Physics B didn't have a lot of rotation stuff in it, but AP Physics 1 does. Plus, there was a lot of schools that took their honors physics and made it AP Physics 1, and they weren't doing rotation. And so they didn't have the equipment for it. And so now we have people needing to do or wanting to do labs in rotation. So what I have is a rotary sensor with the rotational inertia accessory, which comes with 2 identical discs, a hoop, these little catchers. I'll show you what, I think we'll get to it. I'll show you what these are for. And then a pulley. I don't think we'll get to that lab, but I didn't really intend to anyway, that you could use for turning this into a rotational dynamics lab. I'll at least show that. And then this rod with 2 masses on it. And so what I'm going to do is attach the disc with the screw that comes with it. And then now I can spin it. I put a little piece of white tape so you can see that. And then you could do this in front of your class with clicker questions if you had one set, or the lab that I wrote called Rotational Collisions, there's a slide for that later, has these questions sort of embedded in it and students do it themselves. So I'm going to spin that guy and we'll be measuring its angular speed or velocity. And then I'm going to drop a identical disc onto it, and it's going to hit and stick. What's going to happen to the angular speed? And so students can predict that based on other things they've measured. Well, we know we've doubled the rotational inertia because they're identical, so it should go about half. And you can show them that.
And Dan, I gotta interject here. 5-minute warning. 5 minutes.
Okay.
1:55 Central Time.
Well, we're just right on schedule, as always.
Like a train.
So this goes back to one of the first questions asked, how can I tell what sensors are which? Well, now I have 2 rotary motion sensors. And so I just turned the other one on, and it's, I guess the other one turned off. There we go. So that is the correct one, I hope. I hit record and I can spin it. And so it's spinning. And then I drop this. And what did it do? It was going about 30, and then it dropped to 15. Hey, we're right. And that's not too tough a one. The next, we're going to drop the ring. And so if I drop the ring, well, that's not going to turn out too well. So that's what these little catchers are for. And we know they're going to, hey, it's the same mass, right? It's going to be half again, but there's a lot more rotational inertia in a ring than a disc. And so we know that isn't going to be the case. Well, I spun it the other way, but that's okay. There we go. And so it was going about 15 and it dropped to about 5. Well, hey, that's what we predicted. So Scott has given me these time warnings, and then I just realized that he wanted to say a few things here at the end. So you have access to my slides. There's a few more things about the rotary sensor used with this, but I think I got through the best parts here. So I'm going to turn it back to Scott.
All right. All right. Thank you. Thank you, Dan. I'll just take a couple of minutes. Number one, I just posted the workshop evaluation in the chat. So if you would please go ahead and click on that before we close up here in the next couple of minutes. So you'll have that and you can go on and evaluate this presentation. Give me just a moment. I'm going to go ahead and share my screen. Okay. That's what I want to do. Bear with me. All right. So thank you very much, Dan. Just a couple of things in closing up. We want to make sure that everyone knows that some of these great things that you saw with smart carts today, and including some things we did not even show, are available with our new smart cart demo kits. So each one, you just have to choose whether you want the blue cart or the red cart. Otherwise, they are identical, and you get all these great things with a smart cart demo kit. Great things to do in class in front of your students, and they will think you're a wizard because they're so awesome. We've got a lot of physics related wireless sensors, including those smart carts and wireless rotary motion sensors and motion sensors that Dan showed today, smart gates, things like that. I'm always here to answer questions if you have them about incorporating Pasco wireless or wired solutions in your classroom and in your lab.